A grain of sand held at arm's length blocks the same patch of sky as the entire Andromeda galaxy. That single fact shatters our everyday sense of scale, and it's just the beginning. This is a journey through 30 mind-bending comparisons that reveal the true scale of the universe. By the end, you will possess a completely new, visceral understanding of your place in the cosmos, replacing abstract numbers with tangible awe. We will discover what happens when the entire solar system fits on your coffee table, and why the most violent explosions in space make our sun seem like a flickering candle. How does it feel to know that all of recorded human history is less than a final second on a cosmic calendar? Prepare to see reality itself stretched and shrunk through perspectives so extreme they permanently alter how you look at the night sky. What part of this cosmic scale feels most unsettling to you? That glowing marble on the coffee table, our scaled-down sun, holds a secret that makes its emptiness even more profound. Its light, the very energy that powers our world, takes time to cross those miniature gaps. Even in this shrunken model, a beam of light traveling from the sun marble to the Earth speck would take a full 8 minutes to arrive. Think about that for a moment. If our model sun were to suddenly vanish, we on that dust mote would continue basking in its illusory light, orbiting a point of nothingness for 8 long minutes before the sky went dark and our world flew off into the cold. This delay is not a quirk of the model, it is the law of the cosmos. The speed of light, while unimaginably fast to us, becomes a crawl across the true distances of space. It means we never see the universe as it is, only as it was. Every glance at the night sky is a look into the past. The sunlight on your skin left its source 8 minutes ago. The light from Jupiter's peppercorn in our model is already over half an hour old by the time it reaches our eyes. This introduces a haunting cosmic truth. We are forever separated from reality by the speed of information itself, living in a permanent delay of the present. That feeling of connection to our planetary neighbors is further complicated when you realize you are seeing a ghost of where they were, not where they are. This concept of light travel time will stretch to mind-boggling extremes as we leave our coffee table behind. This cosmic delay is the first hint that our solar system is not the center of the stage, but a single performer in a cast of unimaginable size. To find our true place, we must zoom out further, shrinking our entire home galaxy down to a comprehensible scale. Picture the vast expanse of the continental United States, from the rocky coasts of Maine to the sunny shores of California. Now imagine that this entire landmass is our Milky Way galaxy, a sprawling disk of starlight 100,000 light-years across. Within this galactic nation, where would our sun be? If the galaxy is America, then our sun, the blazing heart of our solar system and the source of all life on Earth, is not a major city, not even a small town. It is reduced to the size of a single white blood cell, one microscopic biological defender, adrift in the immense body of a continent. This is the second comparison, and it delivers a profound demotion. Our star is not special by location. It is one of hundreds of billions of nearly identical stars, each a potential sun to its own family of planets, all swirling together in this grand, slow dance. The galaxy transforms from a distant smear in the sky into a teeming metropolis of stellar possibility. Consider the incredible energy and intricate processes contained within a single living cell. Then try to multiply that by 400 billion. That is the dynamism, the sheer raw power contained in our galactic home. This scale does not make our sun insignificant. It makes the galaxy astonishingly, vibrantly alive. It shifts the question from whether other solar systems exist to how many millions of them are out there right now, each with its own story. What does it mean for our search for companionship in the cosmos when the neighborhood is so unimaginably crowded with potential? To answer that, we must leave our galactic continent and look into the vast spaces between these islands of light. Even that galactic continent is not alone in the void. It has a companion, a neighbor whose light we see as a faint smudge in the autumn sky. To understand our place in this local community, picture two ordinary dinner plates. Each one represents an entire galaxy, the Milky Way and the Andromeda galaxy, each plate holding the condensed essence of over 1 trillion stars. Now, place these two plates 25 feet apart in a large, open room. That is the third comparison. Those 25 feet of empty air represent the 2.5 million light-years of profound nothingness that currently separates us. This scale is humbling. Each plate is a swirling metropolis of stellar fire, yet on the cosmic stage, they are practically next-door neighbors, close enough to be gravitationally bound in a slow, inevitable dance. This proximity makes a future headline real. In roughly 4 billion years, these two galactic plates will begin to merge, but forget Hollywood's vision of stars crashing like cars in a pileup. This is a slow-motion ballet spanning hundreds of millions of years. The spaces between stars are so immense that as the galaxies pass through each other, direct stellar collisions will be extraordinarily rare. It is a gravitational tango, where the invisible pull of dark matter and the collective mass of all those stars will weave the two structures into a single, new elliptical galaxy. Our solar system will likely be flung into a new orbit, but the night sky from any surviving planets will transform into a dazzling spectacle of two sunsets as the stars from Andromeda paint new constellations across the heavens. This event underscores a fundamental truth. Galaxies are not solid objects. They are mostly empty space, vast and lonely, with interactions measured in the graceful, patient arcs of celestial mechanics. The 25-foot gap between our metaphorical plates feels small, yet it represents an emptiness so vast it takes light 2.5 million years to cross it. How does it feel to know your galaxy has a date for a merger, and the RSVP was sent by gravity billions of years ago? To comprehend the full guest list for the universe, we must step out of our room and look at the structure of the entire cosmic neighborhood. That galactic merger is just one event within our local neighborhood, a single interaction in a structure of staggering size. To grasp the ultimate container of all this, we need the fourth comparison. Shrink the entire observable universe, every single galaxy, quasar, and photon we could ever detect, down to the size of a common beach ball. This sphere, roughly 93 billion light-years across, becomes something you could hold in your hands. Within that colorful plastic shell, where would our magnificent Milky Way, that continental swirl of 400 billion stars, be located? It would be smaller than a single grain of sand. Not a glittering speck on the surface, but a microscopic mote embedded somewhere deep within the ball's material, utterly invisible to your eye. This is the ultimate reduction. Every image from the Hubble and Webb telescopes, every swirling galaxy and brilliant nebula, all of it fits inside this child's toy. Our entire cosmic horizon, the limit of everything light has had time to reach us since the beginning, is contained within this sphere. The beach ball's surface represents the farthest edge we can see, the cosmic microwave background radiation, which is the cooled and stretched afterglow of the universe's fiery origin. We are not at the center of the ball, we are that invisible grain of sand somewhere inside, with our view limited to the light that has finally reached us. This forces a humbling realization: the universe we talk about, with its awe-inspiring numbers, is just our observable bubble. It is our local view, not the entirety of what exists. The true cosmos, if it is infinite, extends beyond that plastic surface in ways we cannot measure or even comprehend. What lies outside the beach ball? Is it endless emptiness or an infinite repetition of other beach balls, other universes with their own laws? This thought doesn't diminish our bubble. It makes the fact that we can map and understand any of it at all a breathtaking achievement. To build such a map, we must look closer at the grains of sand themselves, at the fundamental architecture of everything we see. Even that cosmic beach ball is not filled with a uniform mist of sand, but with intricate structures, vast gatherings of those galactic grains. To see this architecture, consider a dense swarm of bees hovering over a summer field. This buzzing, living cloud is our fifth comparison, representing a massive galaxy cluster. Each individual bee in that swirling mass is not an insect, but an entire galaxy, a spiral or elliptical island of hundreds of billions of stars. The swarm's overall shape, that teeming, dynamic sphere, is not held together by wings alone, but by invisible forces. For the bees, it is pheromones and communication. For the galaxy cluster, it is the immense, unseen grip of dark matter and gravity. This analogy makes the invisible architecture of the cosmos tangible. We see the galaxies, the bees, but the true scaffold holding them in that specific, coherent formation is completely hidden from our view. The space between each bee is still enormous relative to its tiny body, just as the distances between galaxies within a cluster are mind-bogglingly vast. Yet they move as one unified structure, a single entity drifting through the even greater emptiness of intergalactic space. This is a key node in the cosmic web, where filaments of galaxies meet in dense intersections, with unimaginably empty voids stretching for hundreds of millions of light-years between them. The motion within the swarm is the final clue. Those bees are not still, they are vibrating with life. Similarly, galaxies within a cluster orbit the cluster's center at velocities so astonishingly high that, by all rights, they should fly apart. The fact that they do not tells us something profound. There must be 5 or 6 times more mass holding them in that gravitational dance than we can see in all the stars, gas, and dust combined. This is the primary evidence for dark matter, the hidden skeleton of the universe. The entire swarm buzzes with the energy of that mystery. Can you feel the hum of that unseen force? The gravitational buzz that binds entire cities of stars into a single, drifting continent. To understand how such a structure came to be, we must compress all of time, from the first moment of the swarm's existence to the present day, into a scale we can feel in our bones. The buzzing swarm of galaxies took billions of years to assemble, a time span so vast our minds simply cannot hold it. To feel the true weight of cosmic time, we must compress it into a scale we live by every day. The sixth comparison is the cosmic calendar. Take the entire 13.8 billion year history of the universe from the first moment to this very second and shrink it down into a single calendar year. The Big Bang, the explosive birth of everything, happens at the very first instant of January 1st. In this year-long saga, our Milky Way galaxy does not even begin to form until March. Our solar system, the Sun and its family of planets, condenses from a cloud of gas and dust in early September. Life on Earth remains microscopic for months, with complex plants and animals only emerging in mid-December. The age of the dinosaurs, a reign that lasted over 160 million years, occupies just the final week of the year, from Christmas Day until December 30th. They vanish in a cataclysm on the morning of the 31st. Now consider all of recorded human history. Every pyramid built, every empire risen and fallen, every poem written, every scientific discovery made, every individual life lived from the first cities to you watching this right now. All of it is crammed into the final 14 seconds before midnight on December 31st. Your entire life, every memory you hold dear, flashes by in the last fraction of a blink before the clock strikes 12. This staggering scale, popularized by Carl Sagan, does two things at once. It reveals our profound temporal smallness, showing that humanity is a brand new thought in an ancient, patient universe. Yet it also highlights an astonishing rarity. Our moment of awareness, our capacity to look up and understand this calendar, exists only in these final, fleeting seconds. Every struggle and triumph of our species is not diminished by this scale. It is concentrated into a spark of incredible intensity. We are the universe, after all these billions of years, suddenly waking up and looking back at itself. What do we choose to do with these precious final seconds of the cosmic year? This compression of time forces us to confront a fundamental cosmic rule, one that governs both the vastness of space and the flow of history itself, the absolute speed limit of light. That final blink of the cosmic calendar is governed by a speed limit, a universal rule that defines not just time but the very distances we have been measuring. We speak of light years casually, but to feel their true weight, consider the seventh comparison. A single light year, the distance a photon races through the vacuum in one Earth year, is about 5.88 trillion miles. To make that number tangible, imagine setting out to walk it. At a steady, unbroken pace of 3 miles per hour, you would need to walk for approximately 225 million years. That is nearly 5 times longer than the entire age of the dinosaurs, a stroll that would begin in the Triassic period and end today, with every mountain range you pass eroding to dust and new ones rising in their place. This is not a measure of distance anymore, it is a measure of deep time applied to empty space. It grounds that abstract unit in the relentless plod of a human stride, revealing light's velocity as a miraculous exception to the crawl of everything else. This comparison instantly clarifies why the stars are forever out of reach for travelers like us. The very concept of a journey to another star, with any technology we currently possess, is not a single human endeavor but a project for entire species, a commitment spanning geological epochs. Even if we could shrink our galaxy down to the size of North America, making the distances seem manageable, a single light year on that scale would still be about the length of a football field. Yet to cross that field on foot, in our analogy, would still take millions of years. This frames light not merely as illumination, but as the universe's only patient courier, carrying stories from the past across deserts of time so vast they defy mortal comprehension. Every pinprick of light in the night sky is therefore a historical document, a dispatch from a past so remote that the star you see may have already met its end. How does this reshape your relationship with the constellations? They are not a map of where things are, but a gallery of where things were, each beam a traveler that began its journey long before humans walked the Earth. With this humble footstep as our baseline, we can now attempt the ultimate scaling down, taking the single longest measurement possible, the span from our world to the very edge of everything we can see. That final footstep across a light year defines the longest journey we can conceive, yet it is merely the first step in measuring the ultimate container. To grasp the full scale of that container, we need the eighth comparison. Take the entire observable universe, that beach ball of everything we can see, and stretch its radius out to the size of a major city. Picture the entire diameter of a metropolis like London or New York, spanning dozens of miles from one distant suburb to another. This sprawling urban expanse represents the distance from Earth to the farthest detectable cosmic horizon in any direction, about 46.5 billion light-years. Now, on that same monumental scale, our entire planet Earth, with all its oceans, continents, and 7.8 billion human lives, shrinks down to the size of a single coin. A lonely penny, or perhaps a dime, resting on a sidewalk somewhere in that vast city. This ratio is not just large, it is violently extreme, a difference of over 20 orders of magnitude. Every mountain range, every deep ocean trench, every city we have ever built, all of human civilization and the billions of years of life's evolution before it, are compressed into a metallic disk you could lose between the cracks in the pavement. This comparison does more than humble us. It visually cements the Copernican principle into our bones. We are not at the center of the cosmic city. We are that coin, dropped at a random intersection in a neighborhood we have not yet fully mapped. The metropolis stretches outward in every direction, containing structures and wonders in its other districts that our most powerful telescopes cannot yet see, simply because their light has not had time to reach our tiny, metallic vantage point. What entire galactic civilizations might have risen and fallen in a burrow a few miles over, their stories still traveling toward us at the speed of light. Our entire world is a speck of dust on a grand urban plan we are only beginning to read. To appreciate the full story written on that speck, we must now reverse our perspective and magnify its own deep history, compressing the entire lifespan of our planet into a single human day. That lonely coin of a world holds a story spanning eons, a narrative best understood by compressing it into a single revolution of the clock. The ninth comparison shrinks Earth's 4.5 billion-year history into a 24-hour day, beginning at midnight when the molten planet first coalesces from dust and debris. In this profound day, the first dawn is utterly lifeless. For over 4 hours, the young world is a hellscape of cooling rock and violent bombardment. Then, around 4 in the morning, in the deep, dark waters of a newborn ocean, something flickers. The first simple, single-celled life emerges, a silent, microscopic revolution that will eventually lead to everything we know. Yet for the next 17 hours of this cosmic day, life remains just that, microscopic. The sun arcs across the sky of this allegorical day, and the planet remains a world of microbes. It is not until about 9 in the evening, with 3/4 of the day already gone, that life truly dares to become complex. In the final hours, multicellular organisms explode into existence, filling the seas with strange, early forms. The age of dinosaurs, those iconic giants, does not begin until 10:30 at night. Their magnificent reign lasts for over an hour, a long and dominant chapter, but it ends abruptly at 11:41 p.m. with a sudden, catastrophic event. Now consider humanity's place in this day. The very first human-like ancestors walking upright appear only in the final minute and a half before midnight. All of recorded history, every empire, every invention, every war and work of art, from the pyramids to the internet, is squeezed into the last few seconds. Your entire life, and the lives of everyone you have ever known or read about, unfolds in a fraction of a heartbeat as the second hand sweeps toward 12. This scale does not belittle our achievements, but it frames them within an immense patience. Our world spent billions of years preparing the stage, cycling through countless species and climates, all leading to this fleeting moment of self-aware consciousness in the final instance. It asks a poignant question: how will we use our brief, shining second on this ancient planetary clock? This perspective from deep time makes our current rapid changes feel both incredibly urgent and part of a much longer, resilient story. From this contemplation of Earth's patient biography, we must now turn to a phenomenon that represents the ultimate opposite of patience, a cosmic event of such sudden, violent power that it can outshine an entire galaxy of stars, if only for a few weeks. The patient, billion-year story of our planet stands in violent contrast to a cosmic event that can rewrite a galaxy's history in mere weeks. This is the supernova, a stellar explosion so brilliant it can outshine its entire host galaxy. Yet within our own galactic core lies a different kind of monster, one defined not by brilliant outburst but by a profound, silent hunger. The 10th comparison brings this monster home. The supermassive black hole at the heart of the Milky Way, known as Sagittarius, a star, possesses a mass equal to 4 million of our suns. All that unfathomable weight is crushed into a volume so small its event horizon, the point where gravity's grip becomes absolute, is only about 15 million miles across. To grasp this, picture our solar system with the Sun at its center. Now, replace our Sun with the event horizon of Sagittarius, a star. That dark sphere, the ultimate point of no return, would fit neatly inside the orbit of Mercury. From our earthly perspective, the inner planets Mercury, Venus, Earth, and Mars would all be gone, swallowed by an abyss from which nothing returns. Yet the outer planets, from Jupiter to Neptune, would continue their stately orbits, now circling a perfect, lightless sphere of ultimate gravity. This is the chilling reality. An object with 4 million times the Sun's mass exerts its terrifying influence from a space not much larger than a giant star. It demonstrates the extreme warping of spacetime, where matter is compressed to a density that defies all common sense. The event horizon is not a physical surface you could touch. It is a mathematical boundary in the fabric of reality itself, a one-way door where the laws of physics as we know them cease to apply. From a safe distance, perhaps from Jupiter's perspective, the sky would tell a terrifying story. You would see the background stars lensed and distorted into brilliant rings around a central disk of perfect blackness, a hole in the cosmos itself. The planets would still feel the gentle tug of its gravity, a reminder that this dark heart continues to orchestrate the grand dance of our galaxy from the shadows. How does it feel to know our entire solar system, in all its complexity, could be rendered insignificant by a gravitational pit small enough to fit between the Sun and Mercury? This ultimate compression of matter and energy forces us to look at the opposite end of the cosmic spectrum, the places where matter is born, not destroyed. Against that silent gravitational abyss, nature builds its most magnificent cathedrals of light. The 11th comparison takes us to the Eagle Nebula, and specifically to the iconic pillars of creation. These are not solid structures, but colossal towers of cold gas and dust, light years tall, silhouetted against a backdrop of blistering stellar radiation. If we could uproot this entire formation and place it within our own solar system, the base would sit where our Sun is, and the very tips of those ethereal spires would extend far beyond the orbit of Pluto. Our entire planetary family, from Mercury to the distant Kuiper belt, would fit inside this single, ghostly mountain range. This is the scale of a stellar nursery. Each pillar is a cosmic incubator light years in length, where pockets of denser material collapse under their own gravity to ignite new suns. The sheer dimensional size is staggering, dwarfing any earthly mountain by a factor of billions. Yet here lies the beautiful paradox. These pillars, for all their immensity, are almost perfect vacuums. Their material is so incredibly diffuse that if you were to stand within one, a volume of space the size of your body would contain only a handful of atoms. You would perceive it as a profound, empty darkness, with the glowing walls of the structure so distant they would feel like a far-off nebula in the sky. They are not solid mountains, but fragile sculptures of smoke, shaped and eroded by the very stellar winds of the newborn stars they are creating. How does such a tenuous cloud forge a star? It is a game of patience and collective weight. Across light years of volume, even a few atoms per cubic inch add up to enough mass for gravity to work its magic, slowly drawing the cloud inward until pressure and heat at the core spark nuclear fusion. From near nothingness, a furnace of immense power is born. This leads us to a simple, overwhelming question. If this is the birthplace of stars, just how many of these furnaces are actually shining out there in the cosmic dark? That staggering abundance of stellar nurseries produces a number so vast it defies direct comprehension. The 12th comparison attempts to grasp it by using the most common substance we know. There are more stars in the observable universe than grains of sand on every beach, in every desert, and in every sandbox on our entire planet. The numbers are eerily similar, both hovering around 10 sextillion, a 1 followed by 22 zeros. This means for every single grain of sand you have ever let slip through your fingers, For every dune in the Sahara and every shoreline on every continent, there is a star shining in the cosmic dark. Each of those grains represents a potential sun, many with their own families of planets, their own possibilities for chemistry and perhaps life. This analogy transforms an abstract, astronomical census into a tactile, if still overwhelming, image. Picture standing on a beach that stretches around the globe, its sands deep and endless. Now imagine that beach multiplied across every coastline and arid basin on Earth. That entire planetary collection of silica specks is still outnumbered by the furnaces of hydrogen and helium burning in the void. The universe is not merely large, it is extravagantly, lavishly productive. This cosmic abundance forces a profound question upon us. Does this make the existence of other life, other minds gazing up at their own night skies, feel inevitable, a statistical certainty given so many chances? Or does it amplify the feeling of isolation, knowing that each of those grains is separated from the next by voids so immense that communication across them may be forever impossible? The answer lies not in the number but in the nature of the grains themselves, for each star is not a static speck but a living story with a beginning, a middle, and an end. To understand our own sun's place in that grand narrative, we must compress its entire lifespan into a scale that fits within a single human lifetime. The sun's multi-billion-year story is a biography written in epochs, not moments. To feel the profound difference between its clock and ours, consider the 13th comparison. The entire lifespan of a star like our Sun, from its birth in a nebula to its quiet end as a white dwarf, spans roughly 10 billion years. Now, compress that unimaginable duration down to the single adult day of a mayfly, an insect whose entire conscious world lasts just 24 hours. In this analogy, the Sun's long childhood of gravitational collapse and its fiery, stable maturity, the phase we are in now, would stretch across the mayfly's morning and afternoon. Its final transformation into a red giant, swelling to engulf the inner planets, would be a slow, inevitable sunset beginning in the evening twilight. The mayfly, born at dawn, mates and completes its life's purpose by dusk, never knowing the night that follows. This starkly illustrates the three great clocks of reality. Cosmological time, measured in the lives of galaxies, is the slowest, a deep, patient rhythm. Geological time, the shaping of planets and the rise and fall of species, ticks faster but is still glacial to our senses. Biological time, the frantic pulse of living, breathing consciousness, is the fastest of all, a fleeting spark against the cold dark. From the star's perspective, entire civilizations on orbiting worlds would rise, flourish, transform their planet, and perhaps vanish, all within a single stellar heartbeat. A star might witness its planetary family rearrange, comets shower its worlds with water, and neighboring stars drift apart in the galactic dance. Our Sun has already seen Earth go from a molten rock to a living world. It will watch for billions of years more as life here runs its uncertain course. The mayfly's day is our own human story writ small, a reminder that complex, aware life is not the main event of the universe, but a rare and beautiful side effect of stellar alchemy. This forces a humbling shift in perspective, from the stellar to the subatomic, for the very atoms that allow that mayfly to exist were forged in a furnace far older than the Sun itself. The very atoms that make up the mayfly, the planet, and us are themselves universes of profound emptiness. This leads to the 14th comparison, a classic that reveals a haunting pattern. If you were to scale up a single atom to the size of a major sports stadium, with its nucleus a tight bundle of protons and neutrons sitting at the 50-yard line, that dense core would be no larger than a simple marble. And the electrons, they would not be close by, not even in the lower deck. They would be tiny, buzzing specks moving in a blurred cloud somewhere out in the highest, farthest bleachers. The atom, the fundamental building block of everything you see and touch, is almost entirely empty space. This staggering void within solid matter perfectly mirrors the vast emptiness we find in our solar system, where planets are lonely specks separated by deserts of nothingness. It suggests a fractal truth about reality, where at every scale, from the quantum to the cosmic, structure is defined by tiny knots of concentrated stuff adrift in a sea of void. Your hand, the floor beneath you, the screen you're watching on, all are overwhelmingly empty, held together not by solidity but by invisible force fields, the electromagnetic interactions between those distant electrons and the marble-sized nucleus. This transforms the physical world from something dense and tangible into a dance of energy and probability, a lattice of force that creates the illusion of solidity. How does it feel to know that when you touch something, you are not truly making contact, but feeling the repulsive force between two clouds of electrons that never actually meet? This microcosmic echo of our solar system compels us to look back outward, to find where this pattern of emptiness might repeat on the largest canvas imaginable. This haunting echo of emptiness repeats itself on the grandest possible stage. The 15th comparison reveals a structure so vast it mirrors the most complex object we know, the human brain. When cosmologists map the universe on its largest scales, they do not find a random scattering of galaxies. Instead, they see the cosmic web, a delicate, intricate lattice of brilliant filaments connecting dense clusters of galaxies, all surrounding incomprehensibly empty void. This map bears an uncanny, almost unsettling resemblance to a neural network image of a human brain. The similarity is not merely artistic whimsy. In both systems, nodes of activity, galaxies in one and neurons in the other, are linked by thin threads, gravitational bonds in the cosmos and synaptic connections in the mind. Both networks appear to be organized by a fundamental principle of efficiency, optimizing the flow of something, whether it is matter, energy, or information, across the entire system. The universe's web is a fossilized imprint, the amplified result of tiny quantum fluctuations from the first moments after the Big Bang, stretched across billions of light years by gravity's patient pull. A brain's network is dynamic, shaped by biology and a lifetime of experience. Yet the visual parallel is so strong it forces a profound, almost philosophical question. Are we seeing a universal pattern, a signature way that complex systems naturally arrange themselves, regardless of whether they are made of conscious cells or unconscious stars? Could the universe, in some purely physical, abstract sense, be structured in a way that resembles a mind? This is a metaphorical leap, of course, but a powerful one. It suggests that the laws of physics may inherently produce certain elegant, efficient forms, from the microscopic to the cosmic. This pattern of connection, however, exists within a universe that is not static. The very fabric holding this neural network of galaxies is itself stretching, an expansion that began at the dawn of time and continues to accelerate into the future. That cosmic neural network is not frozen in place, it is being stretched, a process best understood not with abstract equations but with a simple kitchen experiment. The 16th comparison is the universe as a loaf of raisin bread baking in an oven. Picture the raw dough studded with raisins before it goes in. As the bread bakes, the dough itself expands uniformly in all directions. From the perspective of any single raisin, all the other raisins are moving away. A nearby raisin drifts slowly apart, while a raisin on the far side of the loaf recedes much more rapidly. This is not because the raisins are actively crawling through the dough, but because the material between them, the very fabric of the bread, is stretching. This is precisely how cosmic expansion works. Galaxies are not rocketing through a static space. They are largely held in place by gravity within their local clusters, like raisins stuck in their own little pockets of dough. It is the space between these clusters, the cosmic dough itself, that is relentlessly stretching, carrying the galaxies apart, Crucially, from every single raisin, the view is the same, a general retreat of all other raisins. There is no center to the expansion in the bread, just as there is no center to the universe's expansion, no privileged spot from which everything is fleeing. We are all just raisins watching the others drift away as the grand cosmic loaf continues to rise. This gentle, relentless stretching applies to the most immense gaps of all. Consider our local group of galaxies, our little cluster of raisins including the Milky Way and Andromeda, bound together by gravity. Now look beyond our local dough to a distant galaxy cluster billions of light years away. The space between us and them is not merely empty, it is actively growing, stretching the very wavelength of the light, making that journey until it arrives as a faint, redshifted whisper. This means the most distant galaxies we see are not just far away in distance, they are being carried away by the expansion of the canvas they are painted on. How does it feel to be an ingredient in a recipe that has been baking for 13.8 billion years, with no end to the rising in sight? That gentle cosmic rising has a startling and lonely consequence for the distant future. The 17th comparison makes this personal. Think of a dear friend standing on the platform of a train that is just beginning to pull away. You wave and they wave back. For a while, you can still see them clearly, their face, their gesture, but this is no ordinary train. It doesn't just move at a steady speed, it begins to accelerate faster and faster, its engine powered by an unknown, relentless force. The light from their final, fading wave still races toward you across the growing gap. Yet there comes a point, a critical threshold, where the train's acceleration exceeds the speed of light itself. Not the train's physical motion through space, but the expansion of the space between you and the train car. From that moment on, the photons from that last wave are running on a track that is stretching faster than they can move forward. They will never arrive. Your friend has crossed a cosmological horizon, vanishing from your observable universe not by moving through space, but by the space itself carrying them away beyond the reach of light. This is the fate awaiting every galaxy beyond our immediate gravitational family. Driven by the mysterious pressure we call dark energy, it personalizes a profound cosmic isolation. For astronomers in the far future, perhaps billions of years from now, the sky will tell a tragic, incomplete story. All evidence of the cosmic web, the grand neural network of galaxies, will have receded beyond an invisible wall. Their telescopes will see only the dim, aging stars of the merged Milky Way and Andromeda, adrift in a vast, black, and seemingly eternal void. With no clue of the cosmic expansion or the brilliant universe that once was, they might logically conclude their lonely galaxy is all that exists. Dark energy transforms from an abstract parameter in an equation into the architect of a slow-motion farewell to almost everything. This accelerating departure forces us to look back to the opposite extreme, to a time when the entire cosmos was closer than friends on a platform, when everything we see was compressed into a space smaller than a single atom. The profound emptiness we see today was born from a state of almost impossible density. The 18th comparison shrinks the origin of everything down to a simple piece of fruit. In the first trillionth of a second after the Big Bang, the entire observable universe, all the energy that would condense into hundreds of billions of galaxies, was compressed into a region smaller than a grapefruit. Every star, planet, and person you will ever know was once contained within that tiny, superheated volume. This means every point in today's vast, separated cosmos, from the farthest quasar to the screen before your eyes, was once in intimate contact, a unified seed of pure potential. The concept of cosmic inflation, that explosive growth spurt, becomes graspable through this image. That primordial grapefruit expanded to the size of our entire observable universe faster than a thought, stretching the very fabric of spacetime itself and imprinting it with the tiny quantum fluctuations that would later become galaxies. This is the ultimate bridge between scales, linking the uncertain, probabilistic rules of the quantum realm to the majestic, gravitational dance of the cosmos. A single, unified set of physics governed that grapefruit, and it still governs the beach ball universe it became. The contrast with today is absolute. If you took all the matter in the current universe and spread it out evenly, its average density would be almost nothing, about 6 hydrogen atoms per cubic meter. From a grapefruit of pure energy to a cosmic void sparsely sprinkled with atoms, the journey of expansion is the single most defining story of all existence. This explosive beginning set the stage for a slower, more patient force to take over, the very force that would sculpt those initial seeds into the grand structures we now admire. That primordial grapefruit has stretched into a near-perfect void. The 19th comparison makes this emptiness shockingly tangible. If you could take every single atom, every particle of dark matter, from every star in every galaxy across the entire observable universe and spread it all out with perfect, uniform thinness, the average density would be about 6 hydrogen atoms per cubic meter. To feel what that means, look around the room you are in right now. A typical living room's volume would contain only a few dozen atoms drifting in that immense space. Your entire home, from floor to ceiling, would qualify as an almost perfect laboratory vacuum, far emptier than anything we can create on Earth. This is the true default state of the cosmos, a breathtakingly dilute soup. All those dazzling galaxies and brilliant nebulae are not the rule. They are the spectacular exception, tiny, dense knots where matter has miraculously clumped together against the overwhelming trend of emptiness. The majestic cosmic web is not a solid structure. It is the faintest possible tracery of condensation, like frost on a window sketched across an abyss. This realization reframes our own world. Earth is not just a planet, it is a cosmic anomaly of staggering density and complexity, a rare, precious pebble of condensed matter in a universe that is almost entirely nothing. How did such a rich, layered world coalesce from such an unimaginably thin beginning? The answer lies in gravity's patient work, gathering those sparse atoms over billions of years. But gravity can do more than gather. It can crush, creating densities so extreme they defy every law of common sense, beginning with the corpse of a giant star. That near-perfect cosmic void is the birthplace of the universe's most extreme objects, where gravity's victory is absolute. Gravity's patient gathering can turn to violent crushing, forging matter into forms that mock our everyday understanding. Take the corpse of a giant star, a neutron star. Here, the very atoms have been obliterated. An entire star, often more massive than our sun, has collapsed into a sphere barely the size of a city. The matter inside is so incomprehensibly dense that a single sugar cube of it would weigh as much as Mount Everest. This is the 20th comparison. That tiny, sweet lump of crystalline sugar, if it were made of neutron star material, would contain a mass of roughly 1 billion tons. It is not merely heavy, it is a fundamental rewriting of reality. All the empty space that defines a normal atom has been squeezed out. Electrons have been forced into protons, turning them into neutrons, and these subatomic particles are packed together, nuclei touching nuclei, in a single, continuous, unimaginably dense fluid. This is matter stripped to its barest essence, a state that exists nowhere else in the universe under natural conditions. The force required to create this is beyond human engineering. It is the gravitational fury of a star's own core collapsing in on itself after a supernova explosion. To even attempt to hold that sugar cube would be a fantasy. On Earth, its immense density would give it a gravitational pull of its own, and it would slice through the planet's crust like a bullet through tissue paper, accelerating toward the core as if the entire world were made of air. This comparison does more than state a fact. It makes you feel the violent extremity of stellar death. It shows the two possible destinies for massive stars, to become either this ultra-dense remnant or its even more mysterious sibling, a black hole. Both are testaments to gravity's ultimate power to overcome every other force in nature. What strange physics, what exotic states of matter might exist under that relentless neutron-degenerate pressure? We can only theorize from the safety of light years away. To find the brightest beacons that can guide us to such distant wonders, we must now leap from the scale of crushing density back to the scale of staggering distance, to an object whose light began its journey when the universe itself was in its rowdy youth. The journey of light from a neutron star is a brief stroll compared to the marathon undertaken by the oldest photons we can capture. The 21st comparison begins with a number, 13.4 billion years. That is the travel time for the light from the most distant quasars, the hyperactive cores of young galaxies, now reaching our most powerful telescopes. This light is not merely old, it is a direct snapshot of the universe in its tumultuous infancy, a time when the cosmos was less than 1 billion years old. To grasp this timescale in human terms, imagine that ancient beam of light as a single, desperate message. It was emitted into the void at a moment when our sun was a newborn star, and Earth, if it had even coalesced from the primordial disk, was a hellish sphere of molten rock. That message then traveled through the expanding dark, across epochs when continents formed. The first single-celled life sparked in the oceans, and dinosaurs rose to dominate the land. It kept traveling as that dynasty was erased by an asteroid, as mammals took their chance, and as the first human ancestors stood upright. It finally flashed into the lens of a telescope in our modern era, a message sent before multicellular life existed, received by a civilization that builds machines to decode it. This is the ultimate function of light as a time machine. We are not looking back at history, we are watching a live broadcast of creation itself, but with a 13 billion year delay. Every photon from that quasar carries encoded secrets about the conditions of the early universe, the density of matter, the violence of the first supermassive black holes, and the composition of the primordial gas that would become everything we know. We are archaeologists of the present moment, sifting through light that is older than our planet to understand our own origins. What does it say about our place in the cosmos that our most profound discoveries come from messages sent before we, or our world, were even a possibility? That ancient quasar's light is a story of the universe's youth, but our own story of cosmic exploration has barely left the opening page. The 22nd comparison offers a dose of sobering perspective. The Voyager 1 spacecraft, our most distant emissary, has been racing away from Earth for over 45 years. Its speed is staggering, over 38,000 miles per hour, and it has covered a distance of more than 14 billion miles. In human terms, this is an epic, generational journey into the unknown. Yet, to the cosmos, this monumental effort is almost imperceptible. Picture the distance from our Sun to the nearest star, Proxima Centauri, a gap of 4.24 light-years. Now shrink that immense void down to the length of an American football field, 100 yards from end zone to end zone. On this scaled field, with our Sun at one goal line and Proxima Centauri at the other, the entire 45-year voyage of Voyager 1, all 14 billion miles of it, has moved the probe only about 1 single inch away from the Sun's end zone. It has not yet even crossed the chalk of the goal line. This is not a failure, it is a revelation. It frames interstellar space with a brutal, beautiful honesty. Our fastest, most enduring machines are mere crawlers in a nursery that is light years across. The stars are not destinations for our ships, not in any time frame that holds meaning for human civilization as we know it. They are realms for our telescopes, for our physics, and for our boundless imaginations. This scale transforms the question from how we will get there to what it would truly take. Would it require generations living and dying aboard a world ship, or a physics we have not yet discovered. For now, Voyager's 1-inch journey is a testament to both our ambition and our profound confinement. It has, however, reached a frontier defined not by distance, but by the fundamental nature of the universe itself. Voyager's inch of progress takes place on a stage that is itself slowly closing. That cosmic event horizon is not a distant line in space, but a shrinking border in time. Picture our local group of galaxies, our closest cosmic family, as a lone island in a vast, dark ocean. This is the 23rd comparison. The ocean is not still. Its level is rising at an accelerating rate, driven by the mysterious pressure of dark energy. As the waters rise, the visible horizon from our island shore steadily contracts. Distant landmarks, other island chains representing far-off galaxy clusters, one by one slip below the rising tide of expanding space. Their light, struggling against the stretching fabric, eventually finds itself on a current flowing away faster than it can advance. They vanish not with a bang, but with a fading whisper of redshift, lost forever to our view. This is our ultimate causal boundary. Events occurring beyond that horizon cannot ever influence us, and we can never influence them. A perfect and permanent isolation enforced by the geometry of the cosmos itself. The universe is not merely expanding, it is gradually drawing a veil between its distant regions, closing the cosmic curtains on entire chapters of its own story. For future astronomers in our local group, perhaps 100 billion years from now, the night sky will hold a tragic secret. All evidence of the Big Bang, the cosmic web, the existence of other galactic families will have receded beyond an impenetrable veil. Their universe will consist of a single, merged galaxy adrift in an eternal, featureless black. They will have no way of knowing the vibrant, expansive cosmos that once was, no clue to the existence of dark energy. Their island will feel like the entirety of existence. This raises a profound question about the nature of knowledge itself. Are fundamental truths about the universe only knowable during a specific, fleeting window in cosmic history? Our era, where the afterglow of creation is still visible and the web of galaxies still traceable, may be a privileged moment for cosmic archaeology, a brief golden age of observation before the curtains close for good. This isolation plays out not on a static stage, but on the dynamic fabric of spacetime, a medium that can stretch, warp, and even ripple. That curtain of isolation is drawn across a stage that is far from flat and static. The 24th comparison gives this stage a shape we can almost feel. Think of spacetime not as an empty container, but as a vast, flexible rubber sheet. This is the foundational model for Einstein's general relativity, where gravity is not a mysterious pulling force but a consequence of geometry. A massive object like our Sun sits on that sheet, creating a smooth, deep depression, a gravity well. Planets like Earth are not being pulled by an invisible string. They are simply rolling along the curved surface of that well, like marbles circling the rim of a bowl. Their orbits are the natural path of least resistance through the warped landscape. This makes the invisible architecture of the universe suddenly tangible. A black hole, then, is not just a heavy ball. It warps the sheet so severely that it creates a pit with sides so steep they become vertical, forming a bottomless hole from which nothing, not even a rolling marble, can escape. This simple sheet analogy, while a two-dimensional simplification of a four-dimensional reality, transforms our understanding completely. It shows that matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. You are not being pulled down toward Earth's center by a force. You are sliding down the gentle, natural slope your planet creates in the cosmic fabric. Every step you take is a journey across a curved geometry. How does it feel to know you are rolling along a curved surface right now, your path dictated by the dimple your world makes in the universe? This flexible sheet is not perfectly still, however. When massive objects accelerate violently, like two black holes spiraling into each other, they don't just create stationary pits, they send ripples racing across the rubber sheet at the speed of light. These are gravitational waves, the specific wrinkles in the fabric of reality itself. Those ripples in spacetime's rubber sheet are the universe's quietest announcement of its most violent events. The 25th comparison makes their subtlety astonishing. When two black holes, each containing dozens of solar masses, finally spiral together and merge, the cataclysm unleashes more power than all the stars in the observable universe combined, all within a fraction of a second. That energy does not pour out as light, but as a shudder in the very geometry of reality, a gravitational wave that races outward at light speed. By the time this ripple crosses billions of light years to reach our planet, its effect on the fabric of space is almost impossibly delicate. Over a distance of several miles, the wave will stretch and squeeze space by an amount smaller than 1/10,000th the width of a single proton. To grasp this sensitivity, picture the immense gulf between our Sun and its nearest stellar neighbor, Proxima Centauri, that 4.24 light-year void we once scaled down to a football field. Now, imagine measuring a change in that entire cosmic distance by no more than the width of a single human hair. That is the proportional precision required to detect a gravitational wave. Our instruments, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, achieve exactly this. They catch the universe whispering its deepest secrets through vibrations 1,000,000 times smaller than an atom. Every detection is a direct touch of the warped cosmos, a confirmation that spacetime is not a static stage but a dynamic, quivering membrane. It proves that even the most energetic events broadcast their existence not with a scream, but with a faint, precise tremor felt across the ages. What other cosmic conversations conducted in the language of geometry and vibration are flowing through us right now, awaiting a sensitive enough ear? To appreciate the raw power that creates such a subtle signal, we must translate that collision into terms that resonate on a human scale. That subtle tremor in spacetime is a whisper from an event of almost unimaginable fury. A single gamma-ray burst, the most energetic explosion known since the universe began, can unleash more power in a handful of seconds than our Sun will radiate across its entire 10 billion-year lifespan. This is the 26th comparison, and it frames cosmic violence in terms that humble our home star. Think of the Sun's total output as the cumulative warmth and light from a campfire that has burned steadily for centuries, sustaining a circle of life around it. A gamma-ray burst is the instantaneous, planet-shattering flash of a thermonuclear bomb. These events are likely the birth cries of black holes, created when a hypermassive star collapses or when two ultra-dense neutron stars spiral together and merge. For a few fleeting seconds, this single point in space outshines every star in its host galaxy combined, a beacon of raw energy visible across the cosmos. Yet its brilliance is terrifyingly brief, a cosmic stroke of lightning that vanishes almost as soon as it appears, leaving behind an afterglow and a profound question. How does such a titanic, concentrated release shape the space around it? These bursts are thought to sterilize planets in their narrow, focused beams across thousands of light years, potentially resetting the conditions for life in their galactic neighborhood. They are reminders that the universe operates on two extremes: the patient, nurturing fusion of stars like our Sun, and the sudden, catastrophic detonations that can rewrite galactic histories in a blink. While these flashes represent the universe's most dramatic outbursts, they are fleeting. To understand the persistent, hidden architecture of everything, we must now consider a component that never flashes or shines, a ghost that holds the cosmos together. The most powerful explosions in the cosmos are brief punctuation marks against a far more pervasive, silent presence: Our own galaxy, that swirling disk of 400 billion stars, is not floating freely in space. It is held within the gravitational grip of an invisible giant. This 27th comparison gives shape to the dominant, unseen component of our universe, dark matter. Picture the Milky Way's brilliant spiral arms, a disk of light 100,000 light-years across. Now envision a colossal, perfectly spherical ghost, a faint, ethereal sphere of pure mass that completely engulfs that sparkling disk. This is the dark matter halo, and its diameter is not merely larger, it is a staggering 10 times the width of the visible galaxy we see. The entire luminous structure we call home is a tiny, glittering jewel suspended at the heart of this immense, invisible sphere. This is not a metaphor, it is the leading model that explains a fundamental cosmic mystery. Stars orbiting at the outer edges of spiral galaxies move far too quickly. According to the laws of gravity, with only the visible mass of stars and gas to hold them, these stars should be flung off into intergalactic space, like marbles spun too fast on a plate. The fact that they are not tells us something profound. There must be 5 or 6 times more mass holding them in that gravitational dance, mass we cannot see. That missing mass is the dark matter halo, a vast, diffuse cloud of particles that do not interact with light, but whose collective gravity provides the invisible scaffolding for the entire galactic system. Every star in our night sky, including our Sun, orbits within the gentle but all-encompassing gravitational embrace of this unseen giant. We do not feel it, we cannot photograph it, but its influence is the primary architect of the cosmos's large-scale structure. It dictates the speed of galactic rotation, the formation of galaxies themselves, and the very shape of the cosmic web. What is the true nature of this pervasive cosmic ghost that outweighs all normal matter by such a vast margin? Its silent dominance stands in stark contrast to the other great cosmic mystery, the force that seems to be working against it, the dark energy that drives the accelerating expansion of the universe itself. That silent, sculpting gravity of dark matter is locked in a quiet war with its cosmic opposite. The 28th comparison frames dark energy as a mysterious, anti-gravity push. Picture gravity as a patient hand, gently gathering matter into galaxies and clusters, pulling the cosmic structure together. Dark energy is the opposite, a faint but relentless pressure woven into the very fabric of empty space itself. As the universe expands and creates more space, more of this intrinsic pressure appears, causing the expansion to accelerate over time. It is a push that grows stronger as the cosmos grows larger, an engine of separation built into the vacuum. This personifies the two dominant influences shaping our universe's destiny. One is a clumping force drawing matter into islands of light. The other is a stretching force, driving those islands apart on a sea of expanding nothingness. Their tug of war is not a battle of explosions, but of patient, geometric inevitability. For now and for billions of years to come, dark energy's push will win. It will continue to stretch the cosmic canvas, thinning out the grand structures and isolating galactic families behind event horizons of expanding space. This transforms a mathematical symbol in Einstein's equations into an active, enigmatic character in the cosmic story, a presence that dictates the long-term future of everything. What does a universe shaped by this relentless push ultimately become? A cold, dark, and isolated expanse where the memory of a vibrant, connected cosmos fades into permanent myth. To appreciate the full arc of this story, we need to step back and compress its entire timeline into a single, human-scale journey. That silent war between dark matter and dark energy plays out across a timeline so deep it defies our everyday sense of duration. The 29th comparison makes this cosmic history physically imposing. If each single sheet of paper represented 100 years of cosmic history, the entire 13.8 billion year age of the universe would form a stack over 100 miles high, a tower of pages piercing the stratosphere. Each sheet in that impossible column contains a century of cosmic evolution, from the cooling of the primordial fire to the quiet drift of galaxies. The formation of the Milky Way fills reams of paper. The birth and death of countless stars are paragraphs on thousands of pages. The entire 4.5 billion year story of our Earth, from its molten beginning to the age of mammals, would be a sub-stack over 45 miles thick within the larger tower. And human recorded history, all 5,000 years of it, that is a slim half-inch thick booklet resting on the very pinnacle of that 100-mile-high monument. This visual does more than state a fact. It makes you feel the weight of deep time. Our entire collective memory, every legend, every empire, every invention, is a few dozen pages balanced atop a skyscraper of silent epochs. The stories written on the pages near the bottom of that stack are written in a language of physics and chemistry, tales of particle formation, nuclear fusion, and gravitational collapse. They are the foundational chapters of reality itself, composed long before anything we would recognize as a story could exist. This tower of paper is a library of cosmic patience, where the plot only introduces characters like us on the final page. What does it mean to be the authors of that last, thin booklet, suddenly aware of the immense, wordless volumes that support us? Our journey through scale ends not with a distant vision, but with the most immediate experience of the cosmos we all share. That final, towering library of cosmic time is not a distant abstraction, but the very fabric of the sky above you. The 30th comparison reveals the night sky as a grand, silent time-lapse photograph. Each star you see is a snapshot from a different moment in the past, its light a traveler on a unique journey of specific duration. That brilliant blue point of Sirius left its surface 8 years ago. The red glow of Betelgeuse in Orion's shoulder is a 640-year-old message. The faint smudge of the Andromeda galaxy is a 2.5 million-year-old portrait from an era when early human ancestors were just beginning to walk the plains. When you look up, you are not seeing a single coherent now. You are viewing a collage of cosmic history, a palimpsest where the most recent entry might be a decade old and the oldest stretches back to before humanity existed. The familiar shape of the Big Dipper is an elegant illusion of simultaneity, a chance alignment of stellar beacons whose light left at wildly different times, from 50 light years to over 100, all finally converging on your retina tonight. This means you never see the universe as it is, only as it was. Every glance is an act of deep time archaeology, using your own eyes as the instrument. The sky is not a map of locations, but a chart of elapsed times. That faint star might have died in a supernova 1,000 years ago, and its final light is still en route to us, a farewell yet to be delivered. How does this change your next moment under the stars? You are not just looking at points of light, you are reading a layered chronicle, where each pinprick is a chapter from a different epoch, all arriving together in your present moment to tell the single, ongoing story of the cosmos. This final comparison elegantly ties together every scale we have traversed, binding the immensity of space with the depth of time into one inseparable truth. To look outward is always to look backward. Having journeyed from the subatomic to the cosmic, from the first instant to the distant future, we now possess a new framework. These 30 perspectives collectively reveal a universe of breathtaking emptiness and spectacular exception, governed by patient forces and punctuated by violent beauty. They show us that we inhabit a rare, dense oasis in a vast, dilute sea, living in a fleeting sliver of time with the unique privilege to look back and comprehend the epoch that came before. The scale does not diminish us, it contextualizes us. We are the universe after 13.8 billion years of expansion, cooling, and stellar alchemy, become conscious and looking back at itself with wonder. That is the ultimate gift of these comparisons, not a feeling of smallness, but a profound sense of connection to a story grander than any myth, written in the geometry of space-time and the ancient light of dying stars. That layered chronicle of the night sky points to a deeper truth woven through every comparison we have explored. From the stadium-sized atom to the galactic neural network, a profound pattern echoes across reality. The universe seems to operate on a principle of fractal-like repetition, where dense knots of matter and energy are separated by overwhelming emptiness, whether you are looking at the space between a nucleus and its electrons or the voids between superclusters of galaxies. This is not a perfect geometric fractal in the mathematical sense, but a powerful conceptual theme, a signature of how nature organizes complexity across dozens of orders of magnitude. The binding force that keeps an electron in its distant orbit is electromagnetic attraction, while the force that keeps a galaxy tethered to its cluster is gravity, yet both create stable structures within a sea of nothing. This repetition tells us something fundamental about the laws of physics themselves. They are universal, applying the same logical principles whether you are dealing with a single proton or a billion stars. The rules do not change, only the scale and the dominant forces at play. This realization transforms our understanding of scale from a mere catalogue of big numbers into a study of profound relationships. It is about the relative emptiness, the proportional distances, and the repeating architectures that define existence from the quantum foam to the cosmic web. These 30 analogies are not just entertaining facts, they are essential bridges. Our minds evolved to navigate a world of medium-sized objects moving at medium speeds. We have no innate intuition for the lifetime of a star or the size of a proton, so we build conceptual models, a solar system on a coffee table, a galaxy as a continent, to let our consciousness take a tentative step into those alien realms. By walking across these bridges, we do more than learn, we connect. We feel a resonance between the microcosm and the macrocosm, a sense that the universe is not a random collection of parts but a coherent, if unimaginably vast, whole. This journey fosters a unique blend of humility and belonging. We are humbled by our physical smallness and our fleeting moment in deep time, yet we belong to the story because the same patterns that sculpt galaxies are echoed in the atoms of our own bodies. We are made of stardust, yes, but more poetically, we are made of the universe's own recurring architectural style. Perspective becomes the most valuable tool we possess. Our ordinary world is not the default setting of reality. It is just one specific level in an infinite-seeming hierarchy of being, a single page in that 100-mile-high stack of cosmic history. Recognizing this shifts everything. It prepares us to ask the most important question of all, not about the scale of the universe, but about our place within its grand, echoing pattern. The journey through these 30 doorways of perspective leaves us with a single, resonant truth. We have walked from a coffee table solar system to a beach ball universe, from a cosmic calendar to a rising loaf of raisin bread. Each comparison a unique lens bending the light of reality into something our minds can finally hold. The overarching lesson is not one of despair at our smallness, but of quiet awe at our position within it all. We are, by any physical measure, unimaginably tiny and astonishingly recent, specks on a speck in a fleeting second of cosmic time. Yet here we are, creatures of stardust and curiosity, building instruments to catch the faintest tremor in space-time and telescopes to collect light older than our world. We have mapped the invisible scaffolding of dark matter and traced the echo of creation itself. This is the beautiful paradox these scales reveal. Our profound humility is matched only by our profound capacity to understand. As the astrophysicist Janna Levin reminds us, we are the universe's way of knowing itself. These mind-bending comparisons do not diminish our story. They place it within the grandest narrative of all, ennobling our quest and our wonder. Let this expanded perspective linger. Let it color your next glance at the night sky, not as a static tapestry, but as a living, layered chronicle. Let it deepen your appreciation for this fragile, vibrant world we call home. In a cosmos of violent explosions and silent, stretching voids, our moment of awareness is a rare and precious spark. If this journey has shifted how you see your place in the grand story, share the comparison that reshaped your mind the most in the comments below. For more voyages to the edges of understanding, subscribe. Thank you for exploring the true scale of the universe with us.